discussing functional verification regression analysis, the using method using machine learning and a big data method. Abstract. The size of the hardware design increases significantly. The maximum number of regression tests are required to validate functional correctness with the huge amount of the data generated during the design simulation for every test scenario. Debugging regression failure is tedious and a time-consuming task. This paper addressed the challenge of reducing the debugging effort required to validate a design between hardware model iteration on the same design. It proposed the utilization of the clustering machine learning technique to run the design good behavior through the passing regression test. The good test grouped into a test cases cluster such as a buggy test can be detected when it failed the design to any of the identical test cluster in the design regression and test suite. Our framework utilizes the X-means clustering techniques to identify the trace segment, design module name as well as the design signals which are suspected to the culprit of the bad behavior of test. Additionally, our work tackles two main challenges in the learning process. Firstly, signal selection step is done to decide which design signals should be included as tested features during the machine learning phase. Signal selection is based on the signal type as well as the connectivity network. Secondly, big data processing technique, namely MapReduce, is to overcome the challenge of the processing huge trace dump resulted from the design simulation. Our experimental results demonstrate the feasibility of the proposed approach to detect multiple design injection ports using the mutation using with the hardware designs. Introduction. One of the most time-consuming challenge of task in the functional verification cycle is debugging the failure and analyzing the massive amount of data is that produced from the design simulation. Simulation session runs thousands of tests for a long time to exercise the complete behavior of the design. As a result, thousands of gigabytes of the debugging data are analyzed by verification engineers to examine the huge full design trace history and verify repeatedly the result. A critical challenge in the manual debugging effort occurs when the execution result mismatches the reference behavior of the design under verification. The design verification engineer must identify the root cause of a bug and narrow down the problem by recognizing the cycle and the critical design signals involved in the bug occurrence. Clearly, any attempt to automate the bug detection with an execution trace window in which the buggy behavior observed will be of great help to accelerate the debugging effort. Additionally, identifying the design module and the suspected signals which own the buggy behavior will be plus added value. The work elaborates the power of the machine learning techniques to learn the correct design behavior of the passing regression test execution traces. The learned model is then used to differentiate the failing behavior and identifying the trace window and design modules as well as the signals that are root of the buggy behavior. We demonstrate the utilization of distributed big data processing techniques, namely MapReduce, to overcome the challenge of the processing UG traces result from the execution of the long test to the accelerated data encoding steps for ML operation. Finally, we control the number of the design signals to be considered during the feature selection of the ML step using the signal selection algorithms. Signal selection is based on the count of influence (COI) analysis to identify which signal to observe during the design simulation. The rest of the paper is organized as follows. Section 2 briefly reviews the previous work of the analyzing the execution trace for anomaly detection. Section 3 formulated the problem and explained our proposed framework. Section 4 demonstrates the feasibility of our approach against the real design case and explain the use of the mutation testing, our bug injection method. Finally, concluding the remarks and future work the directions is given in section 4. Related work. Recently implemented the design verification strive to automate the error detection process and greatly enhance the engineer abilities to detect functional errors. However, the process of diagnosing the root cause of errors is facing the remains difficult and requires significant manual effort. Many of the previous attempts to bug localization from the dynamic analysis of the hardware design simulation are inspired by a prior work for automatic detection of the software program invariant using dynamic analysis of the program runs, and to few list a few the program runs to list a few. The work on 5 Inferno uses the principle of list astonishment to understand what constitutes the common behavior of the system and use this to detect any anomaly in the design. It analyzes the result of the design simulation traces and automatically extracts a high-level diagram representing the design transaction activity across all the design interfaces. These design diagrams are used for automatic generation of the design checkers that can be used to be detected any future bad changes in the design behavior. The Vogue localization algorithms of the six is based on the statistical analysis of the dynamically converted HDL code items in statement branches and conditions of the processor designs. It presents an approach that is based on the two main iterative phases: dynamic slicing and the statistical linking of the HDL statement and the design that are suspected to be the root cause of the error. And the dynamic slicing error. The dynamic slicing reduces the debug analysis or statement of that actual affect the design faulty behavior of the given stimulus. Then the suspicious ranking assign a suspicion score of each statement present in the dynamic slice. The similar approach is used in the 7 where the information from the regression suite result about the failed and passed test case and the number of statements executed by each test by each test is used to find a highly candidate a statement that be responsible for this incorrect behavior. In this work, we introduced the clustering-based machine learning approach to learn the correct behavior of the design under testing using the entire design regulation passing test cases. And a new failing test case that failed the assignment of any of the learned test cluster is recognized as a bug test. The bug localization module will be identified the bug trace segment time associated with the design modules and the signals related to the detect bug. Our bug leverage the use of the MapReduce method is to accelerate the processing of the user result execution traces from the design simulation during traces encoding and feature extraction for machine learning operation. Figure 1 is ML-based regression test bug detection proposal framework. Proposal framework. Figure 1 describes the major building blocks of the proposed framework. It starts with the RTL regression simulation step. The execution traces are stored in a comma separated value format. The trace dump analyze. The trace dump analyzer processes the trace for the data encoding and feature extraction. The trace dump analyzer is based on the reduced method to speed up the processing of user data resulting to the design or simulation. Clustering machine learning is used to train the cluster modules for the design good behavior using passing regression tests. Once the model is developed, any new test is checked with against the recognized clusters. If the test failed to be assigned to any of the recognized cluster is identified as a bug test. Nearest neighbor classifiers then use assign the buggy traces window to the cluster of the closest label in the feature space. The list of the suspected buggy design signals that detected by the differing the buggy trace window with the nearest labels signal feature. Additionally, the design module name and the trace window number of the observed bug behavior are also reported to verification team. The following subsection is explained in more detail in the main steps in our proposed solution for bug detection modules as described in Figure 1. A. Data preprocessing and feature extraction for a machine learning operation. Clustering is an unsupervised machine learning method. Unsupervised learning is task inferring the hidden structure from unlabeled data. In cluster learning, each cluster is identified by its centroid as well as its shape. The main of the goal of the clustering is to assign a similar input data point to a group, such as all data points with the same cluster and more similar to each other than those in other clusters. Equation 1 demonstrates the typical data set for any clustering algorithms. Typically, a vector of an input data set is X used to extract feature factors H0 xi, H1 xi, HD xi for each input xi, where the D is the number of the input features. The extracted features are then fed to train clustering models, which is going to predict for any future input test case, xi or cluster label assignment. In the problem formulation, the test cases trace dumps are virtually divided into n traces windows where every window has been fixed length of a simulation cycle. A separate clustering model is built for every trace window, where the inputs are regression test case trace window dump, and the features are the number of every signal value changes to 1 within the trace window 9 window. To reduce the number of design signals that are incorporated the feature extraction step, our proposed framework conducted a right RTL static analysis to suppress the design element for such as memories, counters, and equivalent signals and from being included the feature selection step. It focused on the selection of design control signals, FSS data signals, internal registers with a large number of design registers in their cone of influence. According to there is no need to reduce any design signals except the ones to use to trace windows encoding and feature extraction step. Our main goal is to pick up a subset of the design signals with a good probability to propagate to the functional error during simulation. The RTL design is a elaboration at the beginning of the simulation is used to extract some useful static attribution about the RTL under verification, such as signal types, design elements, such as counters, memories, clock order set signals. Curve influence analysis is to done at identifying which design signals are influencing the logic values change for another design signals. Our approach builds signal connectivity graph by identifying recursively the curve influence of each signal each design signal. A standard network analysis algorithm is to run the graph and score signals based on their confluence score. The algorithm uses DFS, depth first search, tree rooted at each design signal and scores each influence by calculating the number of the child nodes. The signals with the influence score greater than a threshold value are picked up for a feature extracted step. To accelerate the feature extraction step, feature extraction is done for all clustering modules all at once using MapReduce. The MapReduce is the framework that was first introduced by Google. It parallelizes the problem that uh, require large dataset processing using a large number of computing nodes. There are many state-of-the-art frameworks to automatically schedule parallel map and reducing num functions in the distribution system to manipulate big input data, and our approach uses our Apache Hadoop. Figure 2 As demonstration how to MapReduce is used for the feature extraction step. The MapReduce consists of three main steps: mapper, shuffle steps, and reducer. MapReduce operation starts by dividing a large trace number file dump file into blocks of 128 megabps. As every data block is assigned to computing node, the list of the design signals whose value arose into a simulation trace dump is stored as a file that is shared among the all processing nodes mapper. The trace of the junk at each mapper is then divided by applying a sliding window of width on the trace sequence as shown in Figure 3. Figure 2 is a map register for a feature extraction step. Figure 3 is dividing the execution into trace windows, and TI is simulation time cycle, and EI is a list of the design signals value changes. The map function of the process is the feature in each individual line in the trace input down window. The design signal values are checked against the previous value. For each signal, if the signal values does not change from each previous value, will not be considered for a feature extraction step. The feature extraction count for the number of the times signal values changes to 1b, the one within the every trace window wi. The mapper will read the trace dump chunks in parallel and emit the key value pair where the key is windows I, wi, and the value is the count of the design signal values changed to one within the window. The map step is to followed by the shuffle step is the Hadoop, thus as it automatically to sort to consolidate intermediate and data from the all mappers and before the reduce task start. During this step, every key and value pair is assigned a computing node as such that all the occurrence of the signal changes for Windows I lands on the same machine. The final step of the reduce step, where the regression sum is done to collect all transition to one, count for every design signal within the same trace window wi. B. Clustering machine learning. The main functionality of the bug detection module is group similar traces windows across the all regression test into clusters, such as a buggy test can be identified as outliers, which fail to assign to any of the identified clusters. In our program formulation, a separate considering module is built to every trace window wi. Clustering machine learning method is aimed to group collecting patterns into clusters based on similarity metrics. Similarity is a measure that reflects the strength of the relationship between the two data items, and it presents how similar two data patterns are. The similarity measure is most applications based on the distance functions such as the Euclidean distance. Generally, there are a lot of clustering algorithms present in the machine learning literature. Our framework utilizes the extension of the traditional k-means clustering method. The objective of k-means is to assign the input data point to the appropriate cluster that minimizes the accumulated distance from each element in the cluster to each centroid. The k-means algorithm starts by the randomization initialization for the clustering centroid. It calculates the distance between every input data point and a k-cluster centroid. The input data is assigned to the corresponding clustering with the minimum distance from each centroid. A second iteration starts by updating the position of the cluster centroid with the region data have been assigned to them in the previous iteration. The new cluster centroids are obtained by calculating the mean of the cluster data points. So the algorithm iterates the assignment of the data point to the new cluster centers followed by a cluster center update until it converges. One of the main challenges in the k-means is to decide on the best cluster count. Our proposed bug detection framework utilizes the x-means clustering algorithms, which is an extended k-means that try to automatically determine the number of clusters based on the statistical score. and Bayesian information criterion (BIC), and I start with only one cluster and goes into action after each run of the k-means, making localization about which subset of the current centroid should be split themselves in order to better fit the data. The splitting decision is by the computing BIC, as explained in 13. Euclidean distance equation is one, as a similarity metric that is used within the k-means clustering algorithms, where Sq and Xk are the feature vectors for the two input data points. The bug localization figure 4 is bug localization algorithms. Figure 4 explains the bug localization algorithm. It starts by splitting the data and the test dataset into multiple trace windows. For all trace windows across the training dataset, X means clustering localization used to group the similar traces windows into same clusters. Once the clustering models are generated, they can be used to predict for any new test whether its windows belong to any of the identified cluster or not. If the trace windows fails assignment, it identifies as a buggy trace window. One nearest neighbor classifier is used to assign the buggy trace window to the class of each closest neighbor in each feature space. The list of the suspected buggy design signals are detected by deferring the buggy trace window with the nearest neighbor signal features. Our method reports the design model name and each signal list and the trace window number for observed buggy behavior. 4. Experimental result. Our experimental result utilized Ethernet MIC IP core downloaded from the 15. The IP core, Ethernet IP core is a Mac mid-access controller as connected to the Ethernet 5 chip on the side of the to the visual associate bus on the others. The training data consists of 1,500 test cases among the different test stage class of the design, namely the register access, the register set, a transmitter packet, the transmitter CRC, and the transmitter receiver. These 1,500 tests were generated by the feeding different seed to the Ethernet constrained by system parallel test bench environment. The test length of the ranges from above the 1 and 1 and 67 to 2 million cycles. The size of the trace dump verifying the fully megabyte up to 5.5 gigabyte, figure 5. Figure 5 is the number of regression tests in the Ethernet across the different testing classes and the size of each test case trace dump in gigabyte. Recall that our workflow created a clustering model is for every trace window. Algorithm uses a trace window of the size 1 or 100 cycles. Table 1 is listed the number of the trace windows extracted from every regression test. The number of windows depends on the trace cycles numbers divided by width of the sliding window, 100 cycles. The clustering step in the approach utilizes X means clustering models to group similar trace window of the WI into a same cluster. X means automatically determine the number of the clusters based on the statistical score, Bayesian information criterion. The maximum number of limit of the clusters X means operation in our experimental works is set to 20. The clustering machine's learning starts with a feature with instruction steps. Our model utilizes number of times the design signals values to change to a 1 within the simulation traces window as well as the main feature metric. In order to reduce the number of the design signals included in the feature instruction step and hence reduce the clustering model complexity. Our framework utilizes COI analysis as well as arithmetic analysis as a main method to select important design signals that have a large number of signals and their cone influence logic of a good probability of the propagated functional error during the simulation. COI score for a given design signal is to define the number of signals to each COI logic. Signals with the influence score greater than a threshold are picked for the feature extraction step. This threshold value is calculated by examining the distribution of design signals, influence scores, and selecting the midway through threshold values to prune the connectivity graph in the first iteration. This process is iterated until the reaching of the threshold values that active a good reduction ratio and sustain a good coverage for design signals. Figure 6 and demonstration COI water distribution for the Ethmac design signals, 2,342 signals. In this experiment, we picked up the threshold values of the 10, which reduced the number of design signals included in the feature instruction, but guaranteed good coverage for design changes during the simulation run. The bug localization module utilized the distributed data processing method, namely MapReduce, to accelerate the design trace processing and the feature of the extraction of the ML modules. During our experiment, we built a Hadoop cluster for nodes as a 3.4 GHz Intel Core i7 and quad-core and a 16 GB per memory. Figure 7 plot the processing time in seconds of the trace dump, encoding the feature extraction steps from the 5 test classes of the Ethernet IP with and without the use of the MapReduce. And Figure 7 demonstrates that MapReduce accelerated the trace dump encoding as well as the feature extraction step by the factor of 2.7 times faster than the essential data processing techniques. The testing dataset has been generated by injecting the bugs to the design RTL using the mutation-based testing techniques. Mutation-based testing originated in the early 1970s in the software research to guide the software testing toward most effective test asset possible. A mutation is an artificial modification of a tested program induced by a fault operator. It changes the behavior of the test program. Our mutation generator creates a set of faulty version of the original description by injecting the one fault above version. These faults are small and syntactically correct modification in the original instruction. The set of the used mutation operators, the mutation signals design modules, signals and the number of bugs injected are listed in the table 2A. The logical and the unary operator mutation are done based on a work published in 17 and summed at table 2B. The judged the effectiveness of a proposed framework to help in analyzing the regression test failure. A group of 40 regression tests across all the test classes have been introduced to the clustering ML framework to identify bug trace window, the name of the bug signals and modules. Module accuracy reflects the ability of the make correct prediction. The accuracy of the created module is judged by counting the ratio of the test for each clustering module managed to detect the exact injected bug success, or to detect a superset of the gene signals that contain the bug signals and other unimpacted signals, partial success, versus the number of times in the clustering the module failed to detect injection bugs and injected bugs into the 40 regression test. Additionally, we calculate the bug detection latency, which is the difference between the cycles where the bugs has been injected versus cycle in which it has been detected. Figure 8 approaches the model accuracy for the test care classes indicated that the average our proposed framework demonstrates on average 81% full success and 13% of partial success and 6% of failure ratio of the models. Ability to detect injected bugs in the design regression test. Additionally, figure 8 indicates the average just 83 the bugs are detected in the same clock cycles on the bug injection cycles. Figure 8 bug detection success in the bug detection latency across all test classes. The conclusion: this paper is proposed a framework that facilitated the functional verification regression test failure analysis. It utilizes clustering the machine learning to learn the design good behavior through the passing the regression test. Good testing grouped into a cluster such as a bug test can be detected when it fails the assignment to any of the identified test clusters of the design regression test suite. The proposed bug detection solution can identify the bug traces, segment time associated with the design module, and a buggy signal list. This technique is used to accelerate the process of the larger generated simulation trace dump during the feature registration step. And we demonstrate an average 2.7 times speedup using the MapReduce versus traditional sequential data processing method. Additionally, our results indicate the bug detection modules managed to detect injected bug with up to 80% accuracy. Thank you.